If you haven't already watched the video on pH titrations, you should do that before you watch this video, since we are going to talk about pH titration curves. This graph shows the pH titration curves overlaid for 3 weak acids titrated with a strong base. What you'll notice is that the 3 acids start out at different pH values. Recall that this initial pH value, before we've added any sodium hydroxide or strong base to the solution, is governed by the weak acid in water ionizing to form its conjugate base and H3O+. So the more H3O+ that is made, the lower the pH will be. The more H3O+ that we make in this equilibrium, the more this equilibrium lies towards products, means that we have the stronger acid. So the lower the pH initially means the stronger acid. And so we can see that this is the strongest acid, and this is the weakest acid. The strongest acid will have the largest value of Ka, and the weakest acid will have the smallest value of Ka. The next thing we can notice is that the pH at the equivalence point for each of these acids is different. And so the pH at the equivalence point for this acid is somewhere around 7. The pH for this acid at the equivalence point is somewhere around 9, and the pH for this acid is somewhere around 10. Remember that the pH at the equivalence point is governed by the base hydrolysis of the conjugate base for the acid that's being titrated. And so this produces OH- in solution, and so we expect a pH that is above 7 or basic. The more basic the solution, the higher the pH. And so we can see that this is the strongest base, and this, with the lowest pH, is the weakest base. Note that the strongest acid correlates with the weakest base, and the weakest acid correlates with the strongest base. And this is exactly what we would expect, since we know that Ka times Kb is equal to a constant Kw. And so as the acid strength, and thus Ka, increases, Kb must decrease, and therefore the conjugate base must be a weaker base. Finally, the volume required to get to the equivalence point is different for each titration. And the amount of base required to get to the equivalence point tells us about the amount of acid we have in solution. And so because all of these titration curves were done with the same starting volume of solution, we know that this acid was the least concentrated, and this acid was the most concentrated, had the most number of moles. Notice that in this case, the weakest acid was the most concentrated, and the strongest acid was the least concentrated, driving home this idea that acid strength and concentration are not the same thing.